we move towards the next one. Concurrent execution, what is mean that we are going to see here. Now see, why we use concurrent execution. Till now we have seen that one transaction is executed, then second one is executed in that case. So what is mean by concurrent execution and why it is important? Now see, concurrent execution means multiple transactions allowed to run concurrently in the system. Multiple transactions allowed to run concurrently in the system. What are the advantages? Improve the throughput and increase the processor and disk utilization. Improve the throughput and increase the disk utilization. Means what? Suppose here there are two transactions are executing, transaction T1 and transaction T2. Now if we execute this concurrently, so in that case it may be possible that transaction T1 is using the CPU while transaction T2 is performing IO operation. Sorry. Okay. So transaction T1 is performing CPU operation while transaction T2 is using IO operation. So in that case, we can say both the transaction can execute simultaneously. So what it increase? It increase the processor and disk utilization. One is using CPU while one is using the IO operation, means performing the disk operation, transferring the block from disk to main memory to disk. So such kind of IO operation another transaction can perform simultaneously. So it improve the throughput. Throughput means the number of transactions which are completed in limited time, that increase. If we execute one after another, then in that case it is not possible. But when we execute both the transactions simultaneously, it improves the throughput. Improve the throughput means the number of transactions that executed in that particular type, it increase that number. Okay. And another important, reduce average response time. Now suppose the transaction T2 is very short of only 4 instructions. Only 4 instructions, and it is a transaction with 50 instructions. Consider that transaction T1 is of 50 instructions and transaction T2 is of 4 instructions. So if we execute serially, first we complete T1 and then we go for T2. Then T2 has to wait until all these 50 instructions are executed. Is it clear? But if we execute it concurrently, then it not necessary T2 to wait. T2 may finish before T1. Why? Because it has only 4 instructions. If it executes concurrently. So reduce the average response time for the transactions. Short transaction need not wait for the long one. Short transaction need not wait for the long one. So these are the two advantages of concurrent execution. And for that, concurrency control schemes are used. 4 different protocols, 4 to 5 different protocols we are going to study in the next part of this unit, such as lock-based protocol, then two-phase locking protocol, graph-based protocol, validation protocol, timestamp-based protocol. So there are some protocols which are used to concurrently control or control the concurrent execution. So that is concurrent execution, or these are the advantages of concurrent execution. Is it clear? Now actual what is meant by serial execution and concurrent execution, that we are going to see. Okay. Now here we consider two transactions as an example. One transaction T1 transfer $50 from account A to account B. Transfer $50 from account A to account B, and that already we have seen that transaction. So it read the value of A is equal to A minus 50, write A, read B is equal to B plus 50, and they write B. Okay. Now T2, transaction T2 transfer 10% of the balance from account A to account B. Now first instruction is read A. Next, what is the next we want to need here? We need to calculate 10% of account A, 10% balance of account A. So here we use a temporary variable. Temp is equal to A multiply with 0.1. Okay. So see here, read A, temp is equal to A multiply with 0.1, where we calculate the 1 minute. Okay. So here it read the 10% balance. So calculate the 10% balance. Remove it from account A. Write the value of A. Read the value of B, and in this way. Now here we consider initially A is equal to 1000 and B is equal to 2000, as we have considered in the last. So see here, we are going to consider these two transactions, and using these two transactions we are going to see what is actual serial execution and concurrent execution. Now see, here we consider the first schedule. Okay, 1 minute. Okay, so serial schedule, what it indicates? Schedule means what? When more than one transactions are executed. So in that case, together we call it as a schedule. So schedule, here we have one schedule is shown here, in which the transaction T1 executed first and followed by the transaction T2. Transaction T1 executed first, followed by the transaction T2. Now again we are going to consider A is equal to 1000 initially and B is equal to 2000. So start with the transaction T1. So what value of A it reads? 1000. A is equal to A minus 50. So what value of A it writes? 950. Then it reads the value of B, 2000. B is equal to B plus 50. Then it becomes 2050. So transaction completed successfully. Last instruction is executed. Values are returned to the disk. Then it enters into the commit state. Commit indicates the transaction completed successfully. Now here, after completion of it starts the transaction T. So it read the value of A 950, calculate its temp means calculate 10%. It's a 10% means temp is equal to 95. Now remove this 95 from 950. So what is the value of A here becomes 855. Is it clear to everyone? So it reads the value of A 950, calculate its 10% 95, then minus this from A becomes 855. Now next it reads the value of B. What value of B it reads? Transaction T2. What value of B it reads? Fast. What value of B it reads? 2050. So it reads the value of B 2050, add 95 here, 2050 plus 95, so it is 2145. So the value of B is here 2145, then transaction is committed. So it first execute transaction T1, then it execute transaction T2. So what is the value stored in the database now? What is the value of A which is stored in the database on the disk? What is the value of A is stored on the database on the disk? 855. Correct. And what is the value of B it stored? 2145. Now calculate its addition. What is its addition? It is 3000. And what is prior to the execution? 3000. So it results in data consistency. What happens here? It executes first transaction T1 and then it executes transaction T2 serially, one after another. So in that case, it result in data towards the next one. That is opposite. First we execute transaction T2 and then we execute transaction T1. So first we execute transaction T2 and then transaction T1. Now again here we consider initially A is equal to 1000, B is equal to 2000. So it read the value of A 1000. Calculate the value of temp. It is 100. Minus it from the A. So A becomes 900. Okay. Read the value of B 2000. Add into the temp. So B is equal to 2100. Correct. See, first it read the value of B 1000. Temp means calculate 10%. Remove 10% from A becomes 900. Then add into the B becomes 2100. Now, after T2, the transaction T1 is executed. Now, what value of A it read? 900 minus 50. So, now A becomes 850. Read the value of B. It read 2100. B is equal to B plus 50. So, B becomes 2150. And then the transaction T1 is committed. So, at the end, what is the value of A? 850. And what is the value of B? 2150. Make its addition. It is 3000. So, before the execution of the transaction, prior to the execution of the transaction, it is 3000. And after the execution, again it is 3000. Means it results in data consistency. It results in data consistency. Okay, clear to everyone? So always remember that the serial execution always result in data consistency. Serial means first we execute the entire one transaction and then we go for another transaction. So the one property of serial execution is that it always result in data consistency. Everyone clear with serial execution? Serial schedule, we call this as a serial schedule. We call it as a serial schedule. Yes or no? So, schedule sequence that indicates the chronological order in which instructions of the transactions are executed in the system. Chronological order means first execute the instructions of one transaction and then another, or the instructions of that particular transactions are executed in chronological order. A schedule for a set of transactions must consist of all instructions of those transactions. Means when we consider a schedule for the set of transactions, here we consider a schedule for two transactions, correct? So it must include all the instructions of these transactions. It must include all the instructions of T2. It must include all the instructions of T1. So a schedule for a set of transactions must consist of all instructions of those transactions. Must preserve the order in which instructions appear in each individual transaction. See again, read must preserve the order in which the instructions appear in each individual transaction. Means what? Whatever the sequence of instructions here, read A, then temp, read B and this. Don't change this sequence. Okay? The instructions must appear in this schedule in the same sequence of this transaction. Similarly, here it appears in the same sequence. Means we cannot perform read B first and read A up later. It must be in sequence. Whatever the sequence, it must be preserved there in the schedule. Read A, then read B. Write A, then write B. So I think it is clear to you what is meant by schedule. Now serial schedule. So serial schedule already I have told you with examples. Each serial schedule consists of a sequence of instructions from various transactions where the instructions belonging to one single transaction appear together in that schedule. So instructions from T2 appear together and instructions for T1 appear together. First T1, then all the instructions of T2. Then we call it as a serial schedule. We execute first T1 all the instructions and then we go for the T2 of all instructions. So that is called as a serial schedule. If there are n number of transactions in the schedule, not necessarily only 2, more than 2 or more. So if there is a set of n transactions in a schedule, then n factorial different serial schedules are possible. N factorial different schedules are possible. So here in this case there are 2 transactions and that's why 2 factorial means 2 combinations are possible. If there are 3 transactions in this, so if there are 3 transactions T1, T2 and T3, then 3 factorial means 6 different combinations are possible. T1, T2, T3, T1, T3, T2, T2, T1, T3 in this way. So 6 different possibilities are there. Everyone clear? So n factorial different possible combinations are there for serial schedule. Now the next and important part of this is concurrent schedule. What is mean by concurrent schedule? If 2 transactions are running concurrently, concurrently means what? See, this question normally asks, what is mean by concurrent? And many times students say simultaneous execution, not actual simultaneous execution. Okay? See, what is mean by concurrent? 2 transactions running concurrently means the operating system may execute one transaction for a little while, means some of the instructions of first transaction, then perform a context switch, execute the second transaction for some time, then execute some of the instructions of second transaction, then again make a context switch back to the first transaction for some time and so on. So concurrent means the operating system execute some of the instructions for first transaction, make a context switch, execute some of the instructions of second transaction, again make a context switch, execute some of the instructions of first transactions and so on. So here one example is given. So here let T1 and T2 be the transaction, whatever we have seen previously, and this is one concurrent schedule. It is not a serial, correct? In serial, one transaction execute entirely and then go for the second. But here, it is a concurrent. What we mean by it executes some of the instructions of T1, then it go for some of the instructions of T2, then T1, again then T2. Now see whether it preserves the consistency or not. One advantage of serial schedule is that it always results in data consistency. But see where this one also preserve the data consistency. Now here again we consider the same. A is equal to 1000, B is equal to 2000. Start with the transaction T1. So it read the value of A 1000. Perform the write operation. So what is the value of A here? It becomes 950. Now what value? Then it make a context switch. Go for the transaction T2. It read the value of A. What is the value of A? It read 950. Calculate its temp. So temp is equal to 95. A is equal to A minus temp. So 950 minus temp 855. Okay. After that, it read the value of B. Again, it make a context switch. Go for the transaction T1. It read the value of B. What is the value of B? It read 2000. Add it into the 50. So here B becomes 2050. B becomes 2050. Again, it is committed. Why? Because the transaction T1 is completed. Now it make a context switch. It read the value of B 2050. Correct? It read the value of B 2050. At temp, what is temp? 95. So B is equal to 2145. B is equal to 2145 and then transaction T2 is committed. See, once again I am explaining. Here it starts with the transaction T1. 3 instructions of transaction T1 are executed. It reads the value of A 1000 initially. A is equal to A minus 50. So A becomes 950. Then make a context switch. Go for T2. Read the value of A 950. Then calculate the temp. It becomes 95. A is equal to A minus. So it writes the value of A, that is 855. Make a context switch, go for the transaction T1, read the value of B. So it reads the initial value of B, that is 2000, add into the 50, B becomes 2050. Make a context switch, go for transaction T2. Now it reads the value of B 2050. Add into the temp, value of temp is 95. So this value is added here, B becomes 2145. Now at the end, what is the value of A? And what is the value of B? See, in database, the value which is written at the end, it is stored in the database. The value which is written at the end by any transaction, that is stored in the database. So what is the value of A at the end? Who performed the write operation at the end? T1 or T2? Who performed the final write operation? T1 or T2? See, it's important when we consider the protocols. So correct. So T2 performed the final write operation. So what is its value stored in the database? 855. Now about the B. Which write the final value of B? Who write the final value of B? T1 or T2? T2. So what it write? It write 2145. So at the end, the final value of A is 855 and final value of B is 2145. When we make the addition, it becomes 3000 and result in data consistency. So we can say this concurrent schedule is result in data consistency. So it is serial schedule. It is equivalent to schedule 1 and schedule 2, which result in data consistency. Next, now see here, this concurrent schedule result in data consistency that we have seen with example, but not every concurrent schedule result in data consistency. Not every concurrent schedule result in data consistency. One example we are going to see here. See, again I am repeating, not every concurrent schedule result in data consistency. Now we consider this schedule number 4, which is also concurrent. Why? It executes some of the instructions of T1, then go for T2 and etc. Now again we here consider A is equal to 1000 initially, B is equal to 2000 initially. Now what value of A it read? 1000. Make it A is equal to A minus 50. Okay, A is equal to A minus 50. What the value of A T2 reads? Anyone? What the value of A T2 reads? Yes, it read 1000. Why not 950? Because here the write operation is not performed 8. Here the write operation is not yet performed by T1 and that's why it reads the original value of A, that is 1000. Correct? Now it compute temp. Temp is equal to 100. Then minus it from A and perform here write operation. So A is equal to 900 here. It performed the write operation. So A is equal to 900 here. See, once again it read the value of A 1000 T1. Then it read the value of A T2. Also the same. Why? Because it not performed the write operation. And that's why it read the original value of A 1000. Calculate temp. Then make it minus. Now here it performed the write A. So A is equal to 900. Now here it performed the write A. Correct? What value it right now? What value of A right now here it? 950, correct. So it here write the value of A 950. Now it read the value of B. What is the value of B? It read 2000. B is equal to B. So write the value of B 2050. Okay. Now before it read the value of B, what it read? 2000. May add into the temp. So B is equal to 2000. What is the value of temp? 100. It is 2100. Okay. So here it write the value of B. See once again, up to this you have seen, write A. It is 900. It read the value of B. Now what value it read? That is 2000. Then here it write the value of A, that is 950. It reads the value of B, 2000 as it is. Perform the 50, add 50, it becomes 250. Write the value of B. Then it perform B is equal to B, temp is 100. So at the end, what is the value of A and what is the value of B? Who performed the final write operation? T1 or T2? Who performed the final write operation? Answer is correct. 950. It write the value of B, A, 950. Why? Because here T2, T1 performed the final write operation. Who performed the final? Not T2, Sakshi. T1 performed the final write operation. Here T2 performed write and then T1 performed the write. So the value which is stored in the database, who performed the last write operation, that value is stored in the database. And that's why here this T1 performed the write A at the end. So value of A is 950. Now who performed? Which transaction performed the final write B operation? So T2 is performed the final write operation. What value it write? 2100. Now make its addition. A plus B 3050. What happens here? It result in data inconsistency. It result in data inconsistency. So that's why we can say that not every concurrent schedule is result in data consistency, but every serial schedule is result in data consistency. Part is serializability. So basic assumption is that each transaction must preserve database consistency. What is our aim? That the database must preserve. This is one of the important characteristics of the database, that it must preserve the data consistency. The serial execution of a set of transaction, always preserve database consistency. But it is not happen in concurrent execution. Some of the concurrent schedules may result in data inconsistency. And that's why we need to identify whether the concurrent schedule, whatever, it is equivalent to a serial schedule. It is equivalent to a serial schedule. We need to identify. And if it is equivalent to a serial schedule, then it results in data consistency. How to identify whether the concurrent schedule is result in data consistency? We check whether it is equivalent to a serial schedule. If it is equivalent to a serial schedule, then we can say it preserves the data consistency. Okay, it preserves the data consistency, and that method is known as serializable. So a concurrent schedule is serializable if it is equivalent to a serial schedule. And if it is serializable, then it preserves the data consistency. See, once again, I am repeating, this is very important concept of concurrency control. The serial execution of a set of transactions is always preserve data consistency. But it is not true regarding the concurrent schedule. So concurrent schedule, if it is equivalent to a serial schedule, if it is equivalent to a serial schedule, then it preserves the data consistency. So for that, what we need to prove? We need to prove that the concurrent schedule, whatever we have written, it is equivalent to a serial schedule, and that is known as serializable. If it is equivalent to a serial schedule, then we call that concurrent schedule is serializable. So there are two different ways in which we can prove that the concurrent schedule is equivalent to a serial schedule or the concurrent schedule is serializable using two methods, conflict serializability and view serializability. So what is conflict serializability? Here we consider that a schedule S in which there are two consecutive instructions I and J. Consecutive means which comes one after another. So we consider that there is a serial schedule. There are two consecutive instructions I and J such that the instruction I belongs to the transaction Ti while instruction J belongs to the transaction Tj. So we consider here Ti and Tj two transactions. Okay, and we consider two consecutive instruction I and J. Two consecutive instruction I and J, where I it belongs to transaction Ti while J belongs to transaction Tj. If this I and J, listen it carefully, it's very important concept. If I and J refer to different data items, means I operate on data item A and J operate on data item B. If I and J refer to different data items, then we can swap I and J easily. Means we write J, first execute J and then we can execute I. Have you understood? See first statement. We consider a schedule S in which there are two transactions or two consecutive instructions I and J refer to the transaction Ti and transaction Tj. If this instruction I and the instruction J operate on two different data items, suppose I operate on A and J operate on B, then we can swap IJ easily without affecting any other instruction. Means I can execute J first and then I can go for instruction I if they operate on two different data items. But if I and J refer to the same data item Q, I also operate on Q, J also operate on Q, then the order in which these instructions execute, it matters. Then the order in which these two instructions execute, it matters. See how with four different cases. There are two instructions, so four different cases are possible. So consider the first case where I is equal to read Q and J is equal to read Q. I is equal to read Q and J is equal to read Q. There are two transactions Ti and Tj. I is equal to read Q and then J is equal to read Q. Okay. Now in this what happens? These two instructions I and J operate on the same data item Q, but it perform only read operation. So can I swap I and J? It is possible. Why? Because this is only a read operation. This is only a read operation. We are not updating the data item Q. That's why I can swap the instruction. I can do J first and then I execute I. It is allowed. So here these two instructions are not conflicting. Okay, not conflict with each other. Now we go for the second. I is equal to read Q and J is equal to write Q. Okay, I write it again. Ti and Tj, or I will. So I again write here Ti and Tj. Now here first I is equal to execute read queue, and then transaction Tj execute j is equal to write queue. So when these instructions are executed in this order, first I and then j. So I cannot read the value which is written by transaction Tj. Correct? Ti cannot read the value which is written by transaction Tj. Why? Because read operation is executed first. Now suppose I perform it in opposite way. I first execute j is equal to write q, and then I execute I is equal to read q. Then here in that case, transaction Ti read the value of q which is written by transaction Tj. Transaction Ti read the value of q which is written by transaction Tj. Is it clear to everyone? See once again, suppose I is equal to read q means transaction Ti perform the read operation and Tj perform the write operation. If first I execute I and then j, first execute read q and then execute write q, then transaction Ti cannot read the value of q that is written by transaction Tj. But if I execute in opposite way, first I execute j and then I execute I. Then in that case, what happens? The transaction Ti can read the value of q which is written by transaction Tj. Means here order matters. Correct? Here order matters. We cannot swap these instructions. We cannot swap these instructions. So we call these are conflicting instructions. And I and j conflict with each other. Now see the third case. Okay. Now in the third case, I is equal to write q and j is equal to read q. I is equal to write q and j is equal to read q, Ti and Tj. Now first I is execute. What is it? Write q, and then j is execute which is read q. So when I execute this in this sequence, what happens? Tj read the value of q which is written by transaction Ti. Tj read the value of q which is written by transaction Ti. But if I execute in opposite way, first I execute, suppose first I execute j, that is read q, and then I execute I which is write q. Then what happens? Tj cannot read the value of q which is written by transaction Ti. Tj cannot read the value of q which is written by transaction Ti, means here order matters. We cannot swap this instruction, and that's why it is known as conflicting instruction. So in this case, these two are also conflicting instruction or conflict with each other. So I write here I and j are conflict with each other. Conflict with each other. Now the fourth case. I is equal to write q and j is equal to write q. See here, both instructions are write instructions. Suppose I execute I first, write q, and then j, write q. Now see what happens here. Both are write instructions. Correct. So when we initially say, we say it is not conflicting. But what value stored in the database? The value stored in the database which is written by last transaction or last execution. So who performed the last execution? J performed the last execution, or the Tj performed the last write operation. So in database, what value is stored? In the database, the value is stored written by transaction Tj. What value is stored? which is written by transaction Tj. If I execute in opposite way, first J and then I. First J and then I. What happens? Which value is stored in the database? Which value is stored in the database? The value which is written by transaction Ti. So, even if both are right operation, the value which is stored in the database, it depends on the transaction which performed the last write operation and which indirectly affect the next read operation, and that's why these are also conflicting with each other. And that's why when we consider these four cases, read, no conflict, only read, no update is there, so we can easily swap the instruction. I read, J write, or I write, J read, it is conflicting. Okay, so the sequence of the instruction matters. We cannot swap these instruction directly. And when both are right, here also the sequence is important. We cannot swap because the value stored in the database is the value which is written by the last transaction, which indirectly affect the next read operation. And that's why in this case also it is conflicting instruction. So when according to these four cases, when it is conflicting, so I and J conflict if they are operations by different transactions on the same data item. They are operations by different transactions on the same data item, and at least one of these instruction is write operation. At least one of these instruction is, at least one of these instruction is write operation. Then we can say I and J conflict with each other. We cannot swap these instructions. Is it clear to everyone? So in that way, using this conflict whatever swapping, we are going to try to convert a concurrent schedule into the serial schedule if it is possible or not. Okay, now we are going to consider this schedule and try to convert it into a serial schedule. Okay, try to convert it into a serial schedule. So I am going to write it here only on this PPT. Okay, now see in this case, read A, write A, T1 perform, then T2 perform, read A, write A. See the same T1 and T2 transaction, but only here read and write operations are used. A is equal to A minus 50, B is equal to B plus 50. That only operations are not considered here. For simplicity, only read and write operations are taken here. Now, here we are going to try to convert this concurrent schedule into a serial schedule by swapping of the instructions. What is the definition of conflict? I and J are the two instructions which execute on the same data item. If these are execute on the same data item, one of this is a write operation, but whether it operate on same data item, if it operate, these two consecutive instructions are operate on different data item, we can easily swap. Here it perform write on A, here it perform read on B. So two different data items are there. So if there are two different data items, we can easily swap these instructions. Correct? Is it clear? So I write it here. Read A, write A. Okay. Then read A. And here I am going to swap. First I execute read and then I execute write. So read B, write A, write B, read B and write B. Okay. Now the next. Can I execute this, swap these two instructions? My screen and whatever I am writing, is it visible to everyone? So tell me, can I swap these two instructions? Yes or no? Can I swap these two instructions? Yes. Why? Because again it operates on two data items. Again it operates on two data items. So in the third stage, I can swap it. T1 and T2. Read A, write A, read A, read B. So I'm going to swap these instructions. So it comes first and then it is next. So here it is write B, write A, and then read B, write B. Okay, now can I swap these two instructions? Yes or no? Can I swap these two instructions? Yes, we can swap. Why? Because these are the instructions which operate on the different data items. So I can swap these two instructions. I write it here only. Okay, so here it comes read B, and here it comes read A. Is it clear? In the fourth step, we swap this. Now, can I swap these two instructions? Yes or no? Anyone else? Only Sakshit and Rohit is giving the answers. What about the others? Can I swap these two instructions? Yes, I can. Why? Because it operates on A, it operates on B. So I can swap these two instructions. So after swapping, write B comes here and read A comes here. So after swapping these instructions one by one in 4 steps, 5 steps, this concurrent schedule is converted into serial schedule. Correct? This concurrent schedule is converted into a serial schedule after swapping non-conflicting instruction. We swap only non-conflicting instruction. We cannot swap a conflicting instruction. So after swapping this non-conflicting instruction, this concurrent schedule is converted into a serial schedule. Then we can say it is a conflict serializable. What we call this schedule? Conflict serializable. Is it clear? So it convert into a serial schedule after swapping non-conflicting instruction means it is preserve the data consistency. Why? Because every serial schedule preserve the data consistency. So the definition of it, simple definition. Okay. So that steps whatever I have previously drawn, it is shown with this PPT. We conflict 1, 2 instructions and then convert into the serial schedule. So if a schedule S can be transformed, a schedule S can be transformed into a schedule S dash. Okay. If a schedule S can be transformed into a schedule S dash by series of swaps of non-conflicting instruction, we say that S and S dash are conflict equivalent, and the schedule S is conflict serializable if it is equivalent to a serial schedule. Is it clear? So in the previous case, we can say that schedule 3 is conflict serializable since it is conflict equivalent to the serial schedule. Since it is conflict equivalent to a serial schedule. Can we swap these two? Sorry. Can we swap these two instructions? No, we cannot swap. Why? Because it both operate on the same data item and one of the instruction is right, and that's why we cannot swap this. Can we swap these two instructions? No, the swapping is not allowed because it operates on the same data item and any one of the instruction or both the instructions are right. And that's why we cannot swap this also and that's also, and not possible to convert into serial schedule. Not possible to convert into a serial schedule, and that's why this whatever the schedule given, current schedule is not conflict serializable. It is not conflict serializable. Why? Because above schedule is not converted into the serial schedule T3, T4 or T4, T3. It is not possible. So I think everyone clear with conflict serializability, so that we can move towards the next part, that is view serializability. Okay. So view as its name, only the view here, not conflicting and all these things are not here. Only we are going to look in the first schedule, concurrent schedule, and the second schedule, and check whether these are equivalent to each other according to the view. So what is view serializable? Let S and S dash be, sorry, let S and S dash be two schedules with same set of transactions. In S there are two transactions T1, T2. In S dash also there are two transactions T1, T2. So S and S dash are view serial equivalent if following conditions, three conditions are met. All the three conditions should be satisfied. Then only we say that S and S dash are view equivalent. What is the first condition? For each data item Q, for each data item Q, if Ti read the initial value of Q in schedule S, then the transaction Ti must read the initial value of Q in schedule S dash. Means we consider this is schedule S with T1 and T2 or Ti and Tj, and the schedule S dash with same transaction set Ti and Tj. If here in this case it from first read A, initial value of A, it read, then in this also the transaction Ti must read the initial value of Q. In this, if transaction Tj read the initial value of B, then in this also transaction Tj must read, 1 minute. Okay. So in this transaction Tj read the initial value of B. Have you understood the first condition? Simple. If transaction Ti read the initial value of Q in S, then in S dash also transaction Ti read the initial value of Q. Now the next one. Okay. So for each data item Q, if Ti executes read Q in S, that value was produced by a write Q operation of transaction Tj. Ti read the value of Q which is written by transaction Tj in S. Then in S dash also Ti read the value of Q which is written by transaction Tj. Again I write here S and S dash. It is Ti and Tj. Ti and Tj. What is given here? In this, if the transaction Ti read the value of Q which is written by transaction Tj in S, then in S dash also Ti read the value of Q which is written by transaction Tj, which is written by transaction Tj. So that is the simple. Next. So in the next, for each data item Q, the transaction that performs the final write Q operation in schedule S must perform the final write in S dash also. So if it is S, it is S dash Ti, Tj, Ti, Tj. So if Tj perform the write Q, final write Q in S, then in this also Tj perform the final write Q operation. Why final write is important? Because that value is stored in the database. So in S, if this one perform the final write Q, then in S dash also Tj perform the final write Q. So these three conditions are satisfied, then we say that S and S dash are view serializable. Then we say that S and S dash are view serializable. So we'll see here the example. It is not view serializable. Both are saying no, that is the correct answer. Why? Because as per the rule of view serializability, if T1 read the initial value of A, then here also T1 must read the initial value of A. But what happens here? Here T2 read the initial value of A. So first condition is not satisfied. Same for read B. Here T1 read the initial value of B, while here T2 read the initial value of B. So first condition is not satisfied. All the three conditions must be satisfied. Second also not satisfied here. Here T2 read the value of A which is written by T1. Here T1 read the value of A which is written by T2, opposite. So second condition is also not satisfied. Third is also not satisfied. Here T2 perform the final write A and final write B. Here T2 perform the final write A and final write B. Here T1 perform the final write A and final write B. So all the three conditions are not satisfied, and that's why it is not view serializable. Is it clear? Schedule 1 and schedule 2 both are not view serializable. Now see this one. Whether these are view serializable, it is view serializable. Why? Because you can observe that here T1 read the initial value of A. Here also T1 read the initial value of A. Here T satisfied. What is the second condition? Whether it is satisfied? Here T2 read the value of A which is written by T1. T2 read the value of B which is written by T1. T2 read the value of A and B which are written by T1. Here T2 read the value of A which is written by T1. T2 read the value of B which is written by T1. So second condition is also satisfied. So here T2 read the values which are written by T1, which are written by T1, and that's why second condition is satisfied. What about the third condition? Here T2 perform the last write A and also last write B. T2 perform the last write A and last write B. Here also T2 perform the last write A and last write B. Means the value which is stored in the database, this one, and here also this one, whatever the written by T2. And that's why the schedule 1 and 2 are view serializable. Yes, it is view serializable. Why? Because here T3 perform the initial read queue. Here also T3 perform the initial read queue. Here T6 perform the final write queue. Here also T6 perform the final write queue. And that's why these two schedules are view serializable. Now whether these are conflict serializable, whether these are conflict serializable, Yes or no? No, correct. It is not conflict serializable. Why can I convert it into a serial schedule? Can I swap these two instructions? No. Both are operate on the same data item and one is right. I can swap this? No, I cannot swap because operate on the same data item, both are right. Can I swap this? It is also not possible. And that's why we cannot convert it into a serial schedule by swapping of the instruction. We cannot swap any instruction. And that's why these two schedules, schedule S suppose and this is S dash, both are view serializable but not conflict serializable. So this schedule is view serializable but not conflict serializable. And that's why the statement is that every conflict serializable schedule is view serializable, but every view serializable schedule is not a conflict serializable. Is not a conflict serializable. Is it clear? So that is about the serializability. Now the next, how to test for conflict serializability. How to test for conflict serializability. So simple method is used here to test whether the schedule is conflict serializable or yes or no. What method is used here? Consider a schedule S with set of transaction T1, T2 to Tn. For that we draw a precedence graph. Graph means directed graph. Construct a directed graph. We call it is the precedence graph. So in the graph we consider two elements. G is equal to V comma E. What is V? Where V is the set of vertices and E is the set of edges. V is the set of vertices and E is the set of edges. So the set of vertices is nothing but the number of transactions which are participated in the schedule. Number of vertices means the number of transactions participated in a schedule. Means if in a schedule there are 4 transactions T1, T2, T3 and T4. So how many vertices are there? There are 4 vertices T1, T2, T3 and T4. Is it clear the first statement? So these number of vertices are there. The set of edges consists of all edges Ti to Tj. So we are going to draw the edges Ti to Tj. In which case the first Ti executes write queue before Tj executes read queue. Means first Ti write queue then Tj read queue. Ti executes read queue before Tj executes write queue. Means conflicting with each other. If it is there, then we can say we draw a edge from Ti to Tj. So if we are going to draw this edge. Now see example. Okay. So in this case, what happens here? There are in the first schedule there are 2 vertices when we draw a precedence graph T1 and T2. So in this case, all the instructions of T1 execute before all the instructions of T2 and that's why there is an edge from T1 to T2. There is an edge from T1 to T2. So in this case also there are 2 vertices T1 and T2. All the instructions are T2 execute first and then all the instructions of T2. So there is an edge from T2 to T1. Simple. It's a precedence graph. In this way we can draw. Now see what is the use of drawing this precedence graph. Why we need to draw this graph? T1 to T2 or T2 to T1. So what is the use of drawing this graph? If we draw this graph for this, it is like this. Because some of the instructions of T1 execute, then T2 are execute here. In this way, it generates a cycle. T1 to T2 and T2 to T1. Now, when we draw such kind of graph, how we can use it for test the serializability. So, if the precedence graph, what we draw for a particular schedule, has a cycle, means as we have seen in the previous, then it is not conflict serializable. It is not conflict serializable. And if the graph contains no cycle, there is no cycle, then it is conflict serializable. That is the simple method used. And for that, different algorithms are used. If there is a cycle, not conflict. If there is no cycle, then it is a conflict serializable. So cycle detection, different algorithms are there. For example, simple depth first search we can use to draw or to check whether there is a cycle or not. Then if there is a cycle, it is not conflict serializable. If there is no cycle, it is conflict serializable. And for that, we can use different cycle detection algorithm based on DFS. Now about the view serializability. To test view serializability, there is not such an algorithm available. Okay, there is no such algorithm available. It is a NP-complete problem. It falls in the class of NP-complete problem. No efficient algorithm is available to test for view serializability. Then how to test the view serializability? Instead of that, concurrency control scheme can still use sufficient conditions for view serializability. It uses some conditions. If these conditions are satisfied, then the schedule is view serializable, otherwise not. But it is not give such kind of accuracy. Why? Because there are some conditions only. Check only some sufficient condition. If it is satisfied, then only it says it is view serializable, otherwise not. Such an algorithm is not yet available for view serializability. So this is about the serializability, conflict and view serializability. To check for which purpose we have studied this serializability, to check whether the concurrent execution it result in data consistency or not. Okay, everyone clear? To check this, we use this conflict serializability and view serializability.